The natural base e. So we have some numbers that are special, such as pi and I. We know pi is the 3.14. It's an irrational number that never ends. And I is equal to the square root of -1. Well, we have another special number. It's called e. E is another irrational number called the natural base, or it's called Euler's number. It's basically the mathematician who discovered it. E is not a variable. E is kind of like pi. So we approximate E at about 2.718 or so. Okay, because this is irrational, like pi, it means it's never ending. Also, like pi, we leave it alone in expressions. We don't change E to its estimated number. We leave E alone as E, just like we leave pi alone as pi. So simplifying natural base expressions. So e to the third times e to the sixth. Now this is not a variable, this is an actual number. But again, we don't want to estimate e. We want to leave e as its full 2 blah, whatever, never ending number. So instead of trying to get an actual number for this, we just use exponent rules. So since it has the same base, e, we can kind of think of this as 2 to the third times 2 to the sixth. Same idea. Since we're multiplying, that means you're going to add the exponents together. So e to the 3 plus 6 power. And 3 plus 6 makes 9. So the simplified version of this is just e to the 9th. We also have division. So 16e to the 5th over 4e to the 4th. So 16 over 4, that's a regular number. So it will simplify down to a 4. 16 divided by 4 makes 4. Now e to the 5th over e to the 4th. Since we are dividing, that means we're going to subtract the exponents. So e to the 5 minus 4. So 5 minus 4 makes 1. So we have 4e to the first, which we can just write as 4e. Now again, this is an actual number. It's not a variable. So example 3. 3e to the negative 4x power all squared. Now we have a variable in here. We have an x. That is an unknown value. E is not unknown. E is about 2.17. So we use the power to a power rule. So this says that we're going to take 3 and square it. And then with this exponent and the outside exponent, we're going to multiply them together. So negative 4x times 2. Well, 3 squared I can evaluate. 3 squared is 9. Now e, negative 4x times 2 makes negative 8x inside the exponent. Simplify with regular exponent rules. Now where do we see e in the real world? So we learned about a previous compound interest. Now I want to make a note here. My previous notes was missing part of the formula. So I'm going to really stress this. With compound interest, when you're compounded monthly, daily, weekly, quarterly, this is your formula. P is the principal, R is the rate, N is how many times you're being compounded, and T is how long you're doing it for. What my previous formula was missing was NT. I will write these again at the very end because you'll need both of these formulas. So that is the compounded at certain times of the year. Now we also have another kind of compounded interest. We have what we call continuously compounded interest. Well, that's when we use a base of E. So A is the value at the end of this compounded period. P is your original. It's called the principal. E is that natural base. R is your rate, so that's the interest rate as a decimal. And T is time, how long are you doing it? Now, it's very important that you remember that E is not a variable, it's a constant. So example 4, you and your friend each have accounts that earn annual interest compounded continuously. So that means we're going to use the A equals PE to the RT formula. The balance A in dollars of your account can be modeled by A equals 45,000 E to the 0.04T. The graph to the right shows your friend's account, modeled over time. So letter A, which has the greater principal? So first we have to remember that principal is the original. Now we find this in two different places. On an equation, my principal is the number in the front. That's the 45,000. So for letter A, my account has a principal of $4,500. On a graph, the principal is found as the y-intercept. That's the original. So on my friend's account, my principal is here at about $4,000. So which account has so let's see, friends is 4,000. So which has the greater? Well, that would be my account. My account has the greater principal in the beginning by $500. Now, letter B says which account has a greater balance after 10 years? Guys, graphs are easier to read than equations. So let's go to the graph. So after 10 years, so that means I want my t to be 10. So find 10 on the x-axis. So this is 2, 4, 6, 8. Here's 10. Go up to the graph. So that would be here. And about how much money will be in that account. Well, these looks like they're going by thousands. 1,000, 2,000, 3,000, 4,000, 5,000, 6,000. So it's a little over $7,000. So I would say about $7,100. $7,100. So my friend's account will have about $7,100 in it. Now I need to figure out my account. Well, my account is that equation. So A equals 4,500 E to the 0.04, and T is a 10. So we're going to evaluate this and see which one's greater. So 4,500 E, 0.4 times 10 is a 4. Then, now remember, E is actually a number, E to the 4th. So E to the 4th is about 54.598. Rounding will make a difference here. Then if you multiply that 54.598 times 4,500, you get about 245,691.68. So the principal difference of $500 made a huge difference after 10 years. Because after 10 years, my friend only has 7,100 and I have 245,000. So my account is larger after 10 years. So in review, here are the two equations or two formulas that you will need. So the compounded interest formula is A is the final amount equals P, the principal, the original, times 1 plus the rate over how many times it's compounded, raised to the number of times it's compounded times the time you're doing it for. Then you have continuously compounded. This is the one that we just worked with. So A again is the final, P is the principal, that's the original, but then we have E to the rate times the time. So it's a lot simpler of an equation. So compounded interest is used when you are doing things like compounded monthly, daily, weekly, annually, things like that. Like you have a time period that you're being compounded. If you see the phrase compounded continuously, you're going to use the above formula. So these are the two formulas that you're going to be using when you talk about compounded interest.